Hello and welcome to lesson 83 in my DP chemistry curriculum. Today we're going over reactivity 2.2.6. This is an HL topic. So this goes over how many reactions occur in a series of elementary steps. The slowest step will determine the rate of reaction. Furthermore, we'll evaluate proposed reaction mechanisms and recognize intermediates, as well as distinguish between intermediates and transition states, and record both in energy profiles of reactions. So what is a reaction mechanism? What are we talking about? Well, what we're doing is we're looking at the steps of reaction because reactions usually occur in steps, individual steps, instead of all at once. They don't just go reactants products. There's usually some steps, and those steps are the reaction mechanism. So furthermore, each step is referred to as an elementary step. With that, these steps aren't necessarily visible, and these are not observable. Observable. Sometimes they are, but most of the time they're not observable, and we know about them mostly through they're hypothesized through both kinetic or energy, kinetic, and stoichiometric data. So we know these steps happen, but it's very hard to often like pause a reaction and see each individual step because as one step happens, it leads directly into the next one. So what does a reaction mechanism kind of look like? Well, let's look at a regular reaction. Nitrogen dioxide plus carbon dioxide, these are both gases, can react to form nitrogen monoxide. Oops, sorry. Nitrogen dioxide and carbon monoxide can produce nitrogen monoxide, also a gas, and carbon dioxide. However, we have found that this actually happens in two elementary steps. So we have step one and step two. The first thing that happens is we actually have two nitrogen dioxides react. And these two nitrogen dioxides react to form nitrogen monoxide, one of our products, as well as nitrogen trioxide, and these are all gases. The second step is this nitrogen trioxide will react with carbon monoxide to form nitrogen dioxide plus carbon dioxide. Again, all gases. And very much like what we did when we looked at enthalpy reactions, is we find these ones that appear on both sides and we can cancel them out. So what we notice is that it's the sum of the steps equal the reaction. So those reaction mechanisms are these steps that lead into the general reaction. Furthermore, you may notice that we have what's called an intermediate. This intermediate is a species that is created and consumed and usually unstable. It's a species created and consumed. And furthermore, it is usually unstable. In our case, in our example, that intermediate was nitrogen trioxide. You see it here and here. It gets created as the product of step one and is consumed as a reactant in step two. Something else we generally want to refer to is something like a rate determining step. So in these reactions, one of these is usually faster. The rate determining step is the slowest of the steps. It's kind of like the weakest link breaks the chain, or the weakest link is the strength of the chain, because this reaction only goes as fast as the slowest step. And so the rate determining step is not only the slowest step, but it determines the rate. reaction. So with all this said, let's do an example practice problem of what you might get. So one possible practice problem might be some reaction. 2A plus B reacts to form A to B. And what you might have to do is find some possible reaction mechanism. And here we actually have two cases. We could do A plus B creates AB, then A plus AB reacts to form A squared B. And that could be step one, step two. In another case, we could do A plus A reacts to form A2, and then A2 plus B reacts to form A2B. We have different intermediates depending on the reaction mechanism we choose. So our intermediate is going to be represented by that circle. These are things that you may be asked to do on a DP exam. All right. So we've talked a little bit about this, but what's the difference between an intermediate, which we are learning now, versus a transition state, which we learned about in our last video? Transition state. So our transition states, which I'm going to refer to as TS, are usually, or not usually, transition states are unstable. You cannot isolate them, cannot isolate them in a reaction. Like in some reaction, we may be able to prove that A2 or AB exists. We may have some type of indicator that reacts with them temporarily, or we may be able to pause the reaction between step one and two and grab a little bit of this. And that's totally fine. These are intermediates. We might be able to get them. But in a transition state, there's no way to pause the reaction. There's no way to get our transition between our reactants and products. We can't pause right between the reactants and products of reaction. Intermediates can be isolated. And while they're usually unstable, they're a little less unstable than our intermediates. A good way to think about it is if you have three podiums, reactants, intermediary, and products. I realize it says RIP, but that's okay. And you are jumping. You are the reactant, jumping. You're flying through the air between each podium. And you can land on that intermediate. That's part of it. But you can't land when you're in the air. So our intermediate is represented right here. That's you. But these little areas where you're midair, you're neither an intermediate or a reactant or a product. These are your transition states. So all you can do is either fall to one or fall to the other, but you cannot be isolated in between. And that's kind of what transition states are in chemical reactions. We can recognize them a lot better in energy profiles. So if we look at energy profiles of a reaction, and we'll just do a simple exothermic reaction. We have our reactants, we have our products. This is a single step. We have no intermediary, we're not stopping anywhere along the way, but our transition state we saw before is right up here. It is that point of highest energy between the activation energy where bonds are broken and they're about to start forming. Meanwhile, we can see intermediaries if we have not single step, a two-step or even a multi-step process. And we'll do another exothermic one. We have our reactants, we have our products, but we have this intermediate phase. And in this case, we actually have two transition states. So we have these transition states going forward, and that's very similar to this reaction right here with the jumping across pedestals. While you're in the air, you're at that highest energy state. That's your intermediates. Or sorry, that's your transition states. So the last thing is we'll just do a little kind of diagram between them. Transition state. We'll do versus a intermediate. So what you really got to know is just transition states. First off, they're high energy states. And we can see that from our energy profile diagram. Whoops, high energy states. They are they have short, unstable lives. Unstable lives. They cannot be isolated, cannot isolate. And they are where some reactant bonds are broken. And products about to form. Products about to form. So we can take our transition states as a guideline for intermediate. These are between two high energy states. Between two high energy states. They are usually unstable. They sometimes can be isolated, sometimes be isolated. And they are where all reactant bonds are broken and no product formed. No product formed. So hopefully this helps you understand a little bit more about reaction mechanisms, intermediates, and transition states, and have a great day.